We've covered several different strategies for identifying causal effects in this class: randomized controlled trials, multiple regression, instrumental variables, and regression discontinuity designs. This week, we'll add one more to our tool belt before the final exam: difference in differences methods. Let's take a look at an example public policy question. Would a lower speed limit on interstate highways save lives?
The national speed limit should be lowered to 55 miles per hour.
55? That's ridiculous! Sure, they'll save a few lives, but millions will be late!
In 1974, the federal government set the national speed limit for interstate highways at 55 miles per hour, much to the chagrin of rock star Sammy Hagar. Over a decade later, in 1987, the government allowed states the option to raise their speed limits to 65 miles per hour. 40 states, including Ohio, raised their speed limit to 65, while other states, like Pennsylvania, kept their speed limit at 55 miles per hour. If we track down some data, we can see that the fatality rate per 100 million vehicle miles traveled in Ohio was 1.45 in 1984, when the speed limit was 55 miles per hour, and 1.25 in 1992, when the speed limit was 65 miles per hour. Does this mean that the increased speed limit caused a 0.2 decrease in the fatality rate? Of course not. Lots of things changed between 1984 and 1992 besides the speed limit. For example, new airbag technologies were introduced that made cars safer. Okay, so what if we make a different comparison? What if we compare Ohio's fatality rate in 1992 to Pennsylvania's in 1992? Remember that in 1992, Ohio had a 65 mile per hour speed limit, and Pennsylvania had a 55 mile per hour speed limit. When we make this comparison, we can see that Ohio's fatality rate was 0.7 deaths per 100 million miles higher than Pennsylvania's. Now it looks like the higher speed limit caused an increase in fatalities. Hopefully, though, you see the omitted variable problem here, too. There are many differences between Ohio and Pennsylvania besides the speed limit, so we can't be sure that the difference in fatalities between them is due to the higher speed limit. We have two different sources of variation in our treatment variable, the higher speed limit. It varies across time. Ohio's speed limit increased from 55 to 65 miles per hour in 1987, and it varies across space. Ohio increased its speed limit and Pennsylvania didn't. Making raw comparisons across time or across space probably doesn't identify the effect of the treatment. But what if we could do both at the same time? This is the intuition underlying what's called the difference in differences strategy. We've already found the fatality rate in Ohio in both 1984 before the speed limit increase and in 1992 after the speed limit increase. We've also found the fatality rate in Pennsylvania, which kept the 55 mile per hour speed limit in 1992. To calculate our difference in differences estimator, we'll need one more number: Pennsylvania's fatality rate in 1984, which was 1.1. Now, we can find the change in fatalities for Ohio, a 0.2 deaths per million mile decrease, and the change in fatalities for Pennsylvania, which experienced a 0.5 deaths per million decrease. Now, we can estimate the treatment effect of the speed limit increase by subtracting Pennsylvania's difference from Ohio's, hence the term difference in differences. In this case, our difference in differences estimator is 0.3, meaning that we can conclude that fatalities in Ohio were 0.3 deaths per million miles higher than they otherwise would have been had the speed limit not been increased. Even though fatalities in Ohio fell between 1984 and 1982, they fell even more in Pennsylvania, which didn't increase its speed limit. This is an example of what's called a natural experiment. To introduce some terminology, we'd call Ohio the treated state and Pennsylvania the control state. To find the difference in differences estimator, we use the control group to approximate the counterfactual path of fatalities in Ohio had they not increased their speed limit. We could also obtain the difference in differences estimator using regression. To start, our data looks like this. We have two states, Ohio and Pennsylvania, each with observations for 1984 and 1992. This data is both cross-sectional and time series, called panel data. Now, let's encode our state variable into an indicator variable that equals 1 for Ohio, and encode our year variable into a dummy that equals 1 for the year 1992. Finally, we need one more variable that indicates the state year observations where the speed limit is 65 miles per hour, which is just Ohio in 1992. Now, we can obtain the difference in differences estimate of the treatment effect by running this regression. We regress our dependent variable, fatalities, on this variable that indicates the treatment, and our state and year dummy variables. Note that the coefficient on the treatment variable here is 0.3, the same as when we calculated arithmetically earlier. Since we have 4 coefficients in our model and only 4 observations, we can't calculate any standard errors, since the residuals are all 0. Now that we can use regression to obtain a difference in differences estimator, we can expand our dataset with more observations. Instead of just one pre-treatment and one post-treatment observation, let's get biannual observations for Ohio and Pennsylvania between 1984 and 1992. Our data now looks like this. Now that we have more than 2 observations per state, we need to add more dummy variables to our regression model, one for each year except one, so that we can avoid perfect collinearity. So our data now looks like this, and our model looks like this. Economists will usually abbreviate all of these year binary variables into a single term when they write out their model, like this. We call this set of year dummies year fixed effects, since they are fixed across states. When we run this regression, we get these results. Again, we see that the speed limit increase had a positive effect on fatalities in Ohio. When we plot out the path of fatalities in Ohio and Pennsylvania, we can see a visual representation of how difference in differences works. We use the path of fatalities in Pennsylvania as an estimate for the counterfactual path of fatalities in Ohio that didn't raise its speed limit. We can then examine the difference between the actual and counterfactual fatalities in each post-treatment year to estimate the treatment effect of the speed limit increase. The coefficient that we just estimated, 0.258, is the average size of each of these differences. We can take difference in differences even further to include more than 2 states. Let's say that New York was another state like Pennsylvania that kept the 55 mile per hour speed limit, and Tennessee increased its speed limit to 65 miles per hour 2 years after Ohio did in 1989. Our 20 observation data set now looks like this. Now we can obtain an estimate of the average effect of the speed limit increase across both Ohio and Tennessee by regressing our measure of fatalities on our treatment variable that equals 1 in the state year observations with a 65 mile per hour speed limit, our set of year fixed effects from the previous model, and a set of 3 dummy variables for 3 of the 4 states in our sample, again dropping 1 to avoid collinearity. Economists will usually write an abbreviation for all of these dummies called state fixed effects like this. This basic setup allows us to use difference in differences to estimate treatment effects for a dataset with any number of units and years. Because the regression includes sets of both state and year fixed effects, this setup is also sometimes called two-way fixed effects. When we estimate the model, we get these results. There's also no requirement that the treatment variable be binary. We could replace this binary variable with a continuous variable that indicates state I's speed limit in year t. This would be particularly useful if, for example, Ohio raised its speed limit to 65 miles per hour, but Tennessee only raised theirs to 60 miles per hour. We can also include control variables so long as they vary by both state and year to avoid collinearity. For example, we could control for each state's population, like this. Looking at the results of this model, we can interpret this coefficient as telling us that each 1 mile increase in a state's speed limit results in an additional fatality per
10 billion
vehicle miles traveled. Difference in differences is an extremely popular method for identifying treatment effects in econometrics for a few reasons. Firstly, it can be very convincing. A two-way fixed effects or difference in differences identification strategy automatically controls for all variables that are fixed across time but vary across states, and those variables that are fixed across states but vary across time. So, for example, we don't need to worry about the effects of business cycles or technological improvements, since those affect all states at the same time. And we don't need to worry about the effects of each state's geography, since geography varies across states, but doesn't vary across time. Another reason why difference in differences is so popular is that the nature of federalism in the United States creates a great degree of variance in state and local policy over time, creating a lot of natural experiments for us to analyze using difference in differences methods. However, as you should be used to hearing by now, difference in differences isn't flawless. There are two big things that can generate misleading results from difference in differences, one of which is much easier to combat than the other. Let's start with the easier problem. In a widely cited 2003 paper, economists Marianne Bertrand, Esther Duflo, and Senthil Mullainathan pointed out that observations within each panel will be more closely correlated with one another than observations between each panel, a kind of serial correlation. This will result in the standard errors when using differences in differences to be understated, leading to researchers using difference in differences to commit too many type 1 errors. By creating fictitious placebo laws, the authors find that difference in differences results in a type 1 error at the 5% significance level as often as 45% of the time, 9 times higher than it should. The solution to this problem is to use an alternative estimator of the variance that accounts for the correlation within clusters, which we can use to calculate what are called cluster-robust standard errors. The formula for cluster-robust variance looks like this, and you can tell Stata to report the cluster-robust standard errors in the regression output by adding this option to the regression command, where this is the variable that defines the clusters. In our speed limit example, this would be the states. When we rerun our previous regression using clustered standard errors, we can see that the standard errors are higher, but still result in statistical significance. In general, you should always use clustered standard errors when working with panel data or performing difference in differences analysis. The other main problem that can affect difference in differences analysis is a bit more insidious. Let's say that we have data on the murder rate in two neighboring counties between 2005 and 2020. In 2013, a pizza shop in one of the counties started offering pineapple as a pizza topping, so we decide to use the difference in differences method to see if pineapple as a pizza topping increased the murder rate in that county. Plotting out the murder rate in each of the two counties, it's pretty clear that the pizza shop's decision had no effect on the murder rate. The murder rate in both the treated and control counties falls as a steady rate in both counties both before and after 2013. However, if we use difference in differences to estimate the treatment effect, we get a big positive estimate. Running a regression confirms this. We get a large and statistically significant effect of the treatment from a difference in differences regression, even though there wasn't any actual effect. So what's the problem here? Well, remember that we are using the path of the control unit as an estimate of the counterfactual path of the treated unit without treatment. If the control unit is a bad approximation of the treated unit, then difference in differences will give an inaccurate result. For example, if our treated county was a large, heavily populated urban area, and our control county was a sparsely populated rural area, then we probably shouldn't trust the conclusion that allowing pineapple on pizza increases the murder rate. How can we know if our control units are good counterfactuals? The key feature we're looking for is called parallel trends. We want the paths of the outcome variables in the pre-treatment period to be parallel. Going back to our pineapple on pizza example, it's clear that the parallel trends assumption is being violated. Murder is decreasing much faster in the control county than in the treated county in the pre-treatment period. So we can't trust our results from difference in differences. If we take a look at our graph from our speed limit example, we can see that the parallel trends assumption is much closer to being met. Fatalities in Ohio and Pennsylvania were falling at about the same rate prior to the speed limit increase. If we're dealing with more than two treated units, then we can't just look at a graph to judge whether or not the parallel trends assumption is being met. One way in which economists can check for parallel trends is to perform what's called an event study, where we run a regression like this, where this variable indicates the year that the treated units switch from being untreated to being treated, and these are lags and leads of that variable, and then plot out the results. For example, the parallel trends assumption is probably met in these graphs, since there's no difference between the treated and control units in the pre-treatment periods, but is probably violated in this graph, since we find big differences between the treated and control units even in the pre-treatment periods. There's software, like the Stata module ESplot or the R package event studies, that can generate these types of graphs for you. Okay, now that we've got a better understanding of difference in differences, let's see it in action in another context. Let's look at a paper by economists Stephen Levitt and John Donohue about abortion that has become well known and controversial even outside of the economics profession. It was even discussed on an Emmy Award-winning TV show. Check it out.
You ever read a book called Freakonomics?
No. What's it about? Bearded ladies and midgets?
Close. It's about economic theory, cause and effect.
Sounds boring.
It's actually a pretty good read. They have this chapter in it. Where have all the criminals gone?
Over there in that field?
In the 1990s, crime fell spectacularly, and this book attributes that to the passing of Roe v. Wade.
Darkness of 73.
The exact opposite, actually. I mean, the abortions that occurred after Roe v. Wade, these were children that weren't wanted. Children who, if their mothers had been forced to have them, would have grown up poor and neglected and abused. The three most important ingredients when one is making a felon. But they were never born. So 20 years later, when they would have been of prime crime age, they weren't there. And the crime rate dropped dramatically.
The show actually does a terrible job of explaining the paper. By this point in the course, you should know that just because abortion was legalized and then crime fell, doesn't mean that legal abortion caused the decrease in crime. Levitt and Donahue, of course, were perfectly aware of this, and actually use a difference in differences design to identify the effect of legal abortion on crime. They're able to do this because different states legalized abortion at different times. Some states, like New York and Washington, legalized it in 1970, while other states didn't legalize it until the Supreme Court case Roe v. Wade 3 years later in 1973. Since the legality of abortion varies across states and across time, we have the two different sources of variation in our independent variable that we need to perform difference in differences analysis. Levitt and Donahue's model looks like this. They regress the natural log of the crime rate in state I in year t on the abortion rate in state I 20 years before year t, state and year fixed effects, and 8 control variables including income per capita, the number of police per capita, and beer consumption per capita. Their results look like this. They conclude that an increase in the effective abortion rate of 100 per 1,000 live births is associated with a reduction of 12% in murder, 13% in violent crime, and 9% in property crime. They also perform a version of an event study to make sure that the parallel trends assumption holds. Notice how there's not a statistically significant difference between the states that legalized abortion early and the states that legalized abortion late in the years prior to and just after those states' legalization. But there's a large difference a few decades later, which means that the parallel trends assumption likely holds. Difference in differences has been used to study the effect of the minimum wage on employment, the effect of monetary policy on bank failures during the Great Depression, and even the effects of mask mandates on COVID-19 transmission. What other uses can you think of? Let me know in this week's discussion board.